All right, guys. This is your week 7 quiz review. All right, so go ahead and make a title on your page in your notes. Make sure you include a page number. Also, add this to your table of contents for week 7 notes if you can. Of course, that depends on where you guys are at. If you've already started week 8 or then you might not be able to do this. But go ahead and just create a page of notes with that title. Okay, so first function thing we're going to look at is a rational function. Okay, so you're going to be given something like this, a graph, and you're going to have to be able to describe key parts of that graph. Okay, so the first thing we want to identify is the asymptote. Okay, and these you could say, almost call them like imaginary lines that create borders or limits within the graph. Okay. Now, what I notice is if I'm looking straight up and down here in the middle of these two hyperbolas, they seem to get really close to +5 here, or where x equals +5, but they don't quite line up. So even if I zoom out, you can see that they kind of really ride right along that line. So the vertical asymptote would be x equals 5 here. Okay, so I notice, and we'll write down what the actual function is afterwards. Okay, so vertical. Okay, and then if I look in the horizontal direction going across here, it kind of has the same thing, except it's at y equals 2. Okay, so the horizontal will always start with a y equals, and then the vertical will start with x equals. Okay, so that's a vertical asymptote, horizontal asymptote. Okay, the other thing we want to look at is what is the function of that? Okay, well, notice here it's at positive x equals 5. Well, let's take a look what the actual function is. It's actually x minus 5 is on the bottom of the function. So with a rational function, there's the other name for this is actually reciprocal, because it's like flipped upside down, is that if that's -5, then in the vertical asymptote is actually +5. So in other words, if I change this to +5, notice how it shifts over to -5. So you got to remember with these functions that x is a liar. Okay, so here I'm going to write in x is a liar. Okay. All right, so and the function for that one is f of x equals 1 over x minus 5 plus 2. So remember that the horizontal comes from that number there, and the vertical comes from that number there. And if that number is negative, then the vertical is positive, whereas if it's positive, then it's negative. Okay? All right, so next one. All right, so now let's look at exponential function graphs. So exponential function. All right, so the first one we're going to look at is f of x equals 3 to the x. Okay, so I'm going to type that in, type in a new function here, 3 to the power of x. All right, so some things we want to describe here are what is the y-intercept. Okay, it was in this case, it's going to cross the y-axis at 0, 1. Okay, and then we're going to look at another function, which is similar. It's going to be 3 to the x, except after that, it's going to say -6. Well, first of all, if you subtract something from a function, what happens to it? Well, let's see. So 3 to the x, and if I put -6, notice how it shifted down. All right. So what is the new y-intercept? Well, it shifts down. It says -6. So it goes from 0, 1 down to 0, -5. So it says shift 6 units down. So even the y-intercept shifts 6 units down. 0, -5. And it shifted down. We'll say the transformation is down 6. Okay. All right, so you're going to be comparing functions and taking a look at what they look like after you've done that shift. So now let's compare some other functions. So let's say I've got h of x, and every time I state a new function, I always use a new letter, is 10 to the x. What does that look like compared to the original 3 to the x? 10 to the x. Notice it still crosses through the y-intercept of 0, 1, but then it's a little steeper. So if it's steeper, that also means it has a faster growth rate. So it grows faster. All right. Now let's say we've got j of x equals 2 to the x. Let's try that. 2 to the x. So there's the original 3 to the x is the red, 2 to the x is the green, 10 to the x is the blue. So it's a little bit less steep. So it's still growing, it's still going up, but it's just going a little bit slower. So we'll say slower growth. So notice if it's a whole number here, or and the number is less than the other number, that's going to be slower, where if it's bigger, it's going to be a faster growth. Okay, so then our next function will be k of x equals 1/2, and we'll put that in parentheses, raised to the x power. So let's see what happens there. 1 divided by 2, and I got to put this in parentheses, and then raise that to the power of x. Now notice that it's going down instead, so it's a decrease in what we call decay. So you got growth going up and then decay going down. And I want you to see how that compares to 2 of x. Notice that they're pretty much opposites of each other, or reflections of each other is what I mean. So here at this point for the 2 to the x, it's 2, 4, and the same point on the 1 over 2, it's negative 2, 4. So it's basically a reflection over the y-axis of that function. Okay, so here, this is going to be a decay or decrease. So now let's turn them all back on and notice what is the same with all of them. They all have the y-intercept of 0, 1. So that's one thing that is the same. Same y-intercept at 0, 1. The only thing that changed the y-intercept was when you shifted it. Okay, if you shifted it over, then that y-intercept changed. But if you don't shift it and you just change the growth rate, that will stay the same throughout all of them. Okay. Okay, so now the next one, let's look at a log function. Okay, so let's say let's start with y equals log of x. Okay, and we're just gonna see what that looks like and then see what it looks like when you move it around. All right, so let's close all these. So now y equals log of x. All right, so first of all, it kind of starts here and see how it rides that line of x equals 0. If you notice, that looks a lot like the problem that we just looked at, like 2 to the x. It's somewhat similar. And if you remember, the base of log 10 is actually, the base of log is always 10 when it's not written. So let's see what happens when we actually write 10 to the x power. Okay, notice they look very similar. It's almost like a reflection and a flip over to this side. It's almost like two reflections. Okay, so it's almost the same, almost looks like the inverse of that function. Notice how this one crosses at 0, 1, this crosses at 1, 0. So these are inverses of each other. But that doesn't matter. We're going to focus more so on the log function itself, but it's very similar. Okay. So first, there's an asymptote here at x equals 0. It doesn't actually cross the y-axis. So it has an asymptote at x equals 0. Okay, it also has an x-intercept, and you'll see that it crosses right here at 1, 0, which if you compare that to these functions, remember the y-intercept was 0, 1. Okay, and the domain, okay, well, the domain, it starts on the left at 0, but doesn't actually get to 0. So what's important to know about that is that since there's an asymptote at 0 and it doesn't actually touch that point, we're going to put a parenthesis. But as it goes to the right, it does keep going forever. So it does keep going this way, okay? So in that case, we put infinity, and remember infinity, we put a parenthesis. And then for the range, it does go down forever, and it does go up forever. I know it doesn't look like it, but as it kind of like goes off in this direction, it is going up just really slowly, and it continually does that forever. All right, so it's going forever in both directions, or infinitely in both directions, up and down. So we're going to use negative infinity up to positive infinity, and we'll use parentheses for both of those. Okay, and the one thing we need to remember too is that the base is automatically 10. Okay, if there's nothing written there, base is automatically 10. And now we're just going to take a look and see what happens when we change things up a little bit. So now let's say I do x minus 2, right? Oops. Notice what changes. Well, first, the x-intercept changed. That's one thing. It shifted over 2 units, and notice I put x minus 2, so remember, x is a liar, so it shifts to the right 2. Also, the asymptote shifted, so now the asymptote's not at 0 anymore, it's at x equals 2. Okay, so if I go the opposite direction, that would be plus 2. Right, so now that x-intercept shifted to negative 1, the asymptote shifted to negative 2. Okay, let's say I subtract 3. Now that shifts down. Okay, and now the x-intercept is way over here. I don't want to keep going and figure out what it is, but it's way over there. Okay, now the y-intercept is shifted down as well. Or actually, there is a y-intercept now, but mainly the idea is that it's shifted down, and those numbers have changed. Okay, so same shifts just like any other function. Okay, next page. All right, now let's look at solving some of these log functions. Okay, so solving with log base 10. Because sometimes we solve these log functions when with different types of bases or different numbers. But in this case, we're going to avoid that and only use bases of 10 in our log. When I say base of 10, that means that we're only using this number, that base of 10. Okay, so now, just like a lot of other problems, I have this number in front of my exponential part, so I'm going to divide that out on both sides, cancel that out. And now it's 5 to the x equals 32 divided by 4, which is 8. So what I could do, and what we'd normally do, is change this to log form. It's an exponential form, and so I'd write log base of 5, and the a value is 8, and that equals x. And then I would evaluate that and calculate that. Okay, but we're keeping everything in the base of 10. So we're not going to do it this way. We're going to do it by keeping everything base in 10. And the way to do that is I'll take the log of both sides. So I can take the log of 5 to the x and the log of 8 at the same time. Okay, so now what I'm going to do next is I'm going to move this x to the front. And there's a rule called the power rule, if you guys remember, that allows us to take the exponent on the a value and move it into the front of the log. Okay, so that's the product. Sorry, not the product, the power rule. Okay, and now I got x over here, So I want to get rid of this log, and I'm going to divide it on both sides. So that cancels. And now what I'm going to have to do is divide log of 8 divided by log of 5. So I'm going to use the scientific calculator for that operation. So type log of 8 divided by log of 5, and there it is. And when you do logs and exponentials, you want to put it to the, you want to round your answer to the nearest thousandth. So 1.292. And honestly, that's kind of an engineering thing. If you ever got into engineering, or if any of you guys are interested in becoming engineers, you're going to be rounding often to the nearest thousandth. Even if you're fabricating something like metal, you're going to be your computers and your use log and exponential functions to estimate those values. And that's why we even have logs and exponentials. By the way, it's all about for things that have to do with like electricity. If you want to be an electrician one day, or design things like that, they use log and exponentials all the time. So anyways, and they round everything to the nearest thousandth because they want it to be super precise. Okay. All right. So the next thing is log rules. Okay. So we have different log rules. And the first one we're going to look at is the power rule, just like we did in the last problem. Okay. So log, we're going to say log base of 6 of x to the 2. And we're going to switch that to a different, we're going to basically expand that out. And we're going to use the same idea of what we did before. We move this x. So we're moving the 2 now. We're going to move that 2 to the front. And it becomes 2 times log base 6 of x. Okay? And again, that's called the power rule. Okay, the next one, let's say that inside the a value is two values being multiplied. So like a number and a variable, 3 times x. Okay, what I can do with that is I can expand it out into 2 different logs. So log base 6 of one value plus, so the key thing here is that you're going to add these two logs. So if you expand it out, you want to add them. And you write the first one, so 3, plus, so basically log base of 3 plus log base 6 of x. So that's expanding out, and that's called the product rule. If you guys remember, product is what you get after multiplying something. So that's why it's called the product, because we're multiplying here. And the other thing I need to emphasize is that you can go back the other way. So let's say you started with this, you can actually squeeze it down or condense it back into the other form. So it allows you to kind of go back and forth in order to help you solve equations. Okay, so now log base 6 of now 3 divided by x. So it's division this time. Okay, so it's very similar to the product rule where I can split it into 2 different logs. Except this time, instead of addition, you do the opposite of that. You subtract. And what's important here is that the number on the top, your numerator, has to go first. You want that to be the first one. And then you're going to subtract the log of the denominator next. So always make sure you put the number on top first and then the number on the bottom second. So that's important. It's not as important here in the product rule. You can actually switch these because you're just adding. But that's like the difference between doing 7 minus 3 and 3 minus 7. Those are 2 different numbers. So you want to make sure you always put the number on top first. Okay, this is called the quotient rule. Okay, the quotient rule. Okay, the result of dividing something, you get a quotient. So that's where that comes from. All right, so now we can use a combination of all these rules. So let's say I have the 3x and the exponent. Well, I can use both of those rules to expand that out. So first, I'm going to use the product rule. I'm going to expand these into 2 different logs. Log base 6 of 3, remember, plus log base 6 of x. And that 2 stays there. So I basically have to the power 2 on both of them. And now, so the first thing I use is the product rule. So product. And then I'm going to expand it more by moving the 2's to the front of the logs. So now they're both 2 times log base 6 of their values. So 2 log base 6 of 3, and then 2 times log base 6 of x. Okay, and that, again, was the power rule. Okay, so you can use these to kind of expand them out, and you can go back the other direction too, or what we call condense them. Okay. All right. So next one. So now let's use this rule to solve an equation. Oops, I don't want that. Okay, so let's see. Say I've got log of 5 plus log of x equals log of 30. Notice I did not write a base, so automatically those are tens. Okay. Now what I can do is I have 2 logs being added and they have the same base, and it's important to note that they must have the same base. So if this was like, 10 and this was 6, I can't add them together. Like I can't combine or condense them. Because they're being added, that means I can use the product rule to bring them together by multiplication. So now I'm going back the other direction. I'm going backwards from what I showed you guys just now. Okay, and then I've still got log of 30 here. Okay, so there I just used the product rule. Now I've got 2 logs equal to each other. When you have 2 logs equal, I can cancel them out. And so the a values must be equal to each other. So now it's just 5x equals 30, divided by 5. So x must equal 6. Okay? So here the logs cancel. Now the thing is, the logs, guys, will only cancel if you have 1 log on each side. So if you've got 2 logs over here, you can't just cancel them all because it's not equal to 5 plus x equals 30. You have to combine all the logs on one side and the other side, so you have to have 1 log on each side. Sorry. Okay. All right. Last one here. So this is a little review of radical or square root functions. You guys have done these before, but I want to review it because I constantly have been seeing mistakes with it. So I just want to make sure you guys are good with these, or at least getting better with them. Okay, so now I'm going to remember to solve these. You want to square both sides. Okay, so remember when you square them, the radical disappears. So you just have x plus 18. Now, you got to be careful here. This is not equal to x squared plus 4 or x squared plus 2. You don't just distribute the square, okay, or x squared minus 2 or 4 or whatever. These are not how you multiply those out. Okay, if this says squared, this means that you have 2 x minus 2's or x minus 2 written twice. Okay, so in order to multiply that out, I'm either going to FOIL it, if you guys remember how to FOIL, or I'm going to use the box. And when you use the box to multiply, you put your factors on the outside. And then your terms will be on the inside. So x times x, x squared, negative 2 times x, negative 2x. Same thing here, negative 2x. Negative 2 times negative 2 is positive 4. Okay, so now I write my first term, x squared, and I want to combine the like terms, and the only 2 like terms are these two, the negative 2x and negative 2x, so that would add up to negative 4x, and then I have positive 4. And so I just bring down the left side of the equation. And now remember, when you have x squared, you want everything to equal 0. Okay? So we'll say, where are we going to put this? Make it equal 0 when there is x squared. Okay, so to make it equal 0, I need to take away the x and the 18 on this side. So minus x and minus x here to the like term, minus 18 minus 18 to the other like term. Those cancel. Then I have bring down the x squared. Negative 4 times, or minus x is minus 5. 4 minus 18 is negative 14. All right, so now what I want to do is solve quadratics. Remember that we need to factor it out, so that means we're going to use the x in the box. Okay, so on the top, it's your a times your c, so negative 14x squared. On the bottom, it's your b, so negative 5x. Okay, and looking for those two numbers that multiply to negative 14, add up to negative 5. That would be negative 7x and positive 2. Okay, so now I put those inside the box. And remember, your first term of the equation you're solving goes in the first box. Your last term goes in the last box. And the two numbers you found go in the other boxes. And it doesn't matter where you put them. You can put the 7 here, the 2 there. It doesn't matter. So the first one that's always easy is when it's just x squared, x times x gives me that value, or that term. And then you just fill in the rest. So now x times positive 2 gives me 2x. And then x times negative 7 gives me negative 7x. So now I fill that in. So x plus 2 and x minus 7. Okay, zero product property says that if that's positive 2, my first solution is negative 2. And if that's negative 7, then my answer is positive 7. Now here's the deal. When you're dealing with these radical functions, you need to check if they work, because one of these may not work. One of them may be what's called extraneous, okay? So we'll say check for, extraneous. Okay, so I'm going to first start with the positive 7, okay? So I'm going to plug in positive 7, so it's 7 plus 18, or the square root of 7 plus 18, equals 7 minus 2, because there's x on the other side too. Okay, so this will be 7 plus 18 is 25, so square root of 25. The 7 minus 2 is 5. And the square root of 25 is 5, so that one works. Okay, so now let's plug in the negative 2. So negative 2 plus 18, and then negative 2 minus 2 on this side. Okay, so negative 2 plus 18 is positive 16. Negative 2 minus 2 is negative 4. Well, the issue here is that the square root of 16 is positive 4, not negative 4. So that means that this is not a solution. Now, some of you guys might be like, wait a minute, coach, but you guys always tell us if we square root something that it's both positive and negatives. Why is it not here? Okay, well, here's the deal. Let's say I'm dealing with that kind of problem, right? Let's say I had, problem like this, right? I add 9 both sides, and then it's x squared equals 25. I square root both sides, and x equals 5. And you're like, well, if I square root, that means that it's also negative 5. Right. It is positive and negative. But now plug that back into the function and see if it works. Okay, so now if I plug 5 back in, well, 5 squared minus 9. And then let's plug in negative 5 squared minus 9 equals 16. Okay, so this would be positive 25 minus 9 equals 16. That works. And if I plug in here, that becomes positive. So that also works. So notice what happens when you plug it into a function that is squared. It's going to become positive, so it always works. Whereas if it's a radical function, when you square it, it's going to be positive when you check it. So that's the reason why, is that so if I plugged in all those other problems, it would work. But for these problems, it doesn't always work. So you need to check it. So in this case, x equals 7 is my only solution. Okay, so make sure you're always checking your answers on those radical functions. Okay, that's it.